So my screen is appearing above. Is it clear?
Yes, sir.
Okay.
Yes, sir.
So today we are going to start with the new unit, design of joints. So this design of joints contains the three topics. Three topics. The first one is the fourth unit, design of joints. Joints. The first one, quarter joints. Quarter joints. The second one, riveted joints. Riveted joints. The third one, welded joints. So this fourth unit also, this total fourth unit, you need to remember the entire design procedure like a couplings what we discussed in the previous topic. On an average, just wait, your friend is coming. Somebody is coming and lifting the class. So on an average, total how many? 12 to 15. 12 to 15 design procedures you need to remember. Total 12 to 15. Okay. So if you remember this 12 to 15 design procedures, I'm telling procedure, design procedure. If you remember this design procedure, so same like in shaft coupling, what I said, no need to practice the numericals also, right? So here, design procedure is a very important, particularly this fourth unit. Don't forget this one. So the first topic I'm discussing now, quarter joints. So quarter joints. The first topic is a quarter joint. So what is a quarter? Quarter is a nothing but it is a rectangular piece of metal. It is made of a mild steel or birth iron. So based on the requirement, material is going to select it. It is a rectangular piece of metal. Okay. So with this joint, with this piece of metal, the joint is going to done for the coaxial rods or bars, coaxial bars or two shafts, which are subjected to the tensile forces or compressive forces. So see here the quarter is a flat wedge shaped piece of rectangular cross section, having the rectangular cross section, and width is tapered. Its width is tapered on the either one side or both sides. Okay, for easy adjustment, removing insertion purpose. And the made material selection for this one, mild steel or wrought iron, and it is a temporary fastening to join the two coaxial rods or coaxial bars or shafts, which are subjected to, this is the point very important, which are subjected to the axial loads or compressive loads. These are very important. Where we can find such application for this quarter joint, we can find in a reciprocating steam engines, a piston rod and it extension as a tail or pump rod or strap end of the connecting rod. In this situation, we can find this kind of quarter joint application. So this is the brief introduction about the quarter. Okay, you may expect this slide for the 2 marks question. And coming to the types of quarter joints. Quarter joints are three types: socket and spigot joint, sleeve and quarter joint, gib and quarter joint. Right, these three are the main as per your syllabus. So today I'm going to discuss about the first topic, the socket and spigot joint. So what is a socket and spigot joint? The see the figure is appearing here, the front view and the side view and the cross sectional view. This is a cross sectional view, this is a front view, and this is a top view. So socket is nothing but one hollow type of portion, and spigot is a having a solid rod. Both are inserted in this manner, right? And one rectangular groove hole is created. Through that hole, the cotter is inserted. So for joining these two rods, cotter is using. So that's the
Sir,
reason. Yeah,
I can see the whiteboard, sir. Means I cannot see the picture.
you cannot see the picture.
In starting, you wrote three types of joint, no, sir. That is only visible.
Maybe from your side problem already I shared just right, but again I'm sharing. Now is it appearing?
Yes, sir.
Right? So cotter joint is socket and spigot cotter joint means here socket means a hollow portion provided with the socket type. Okay, and spigot means a continuous solid rod. Both are inserted. See, you can see the cross sectional view. The upper portion, the upper portion is referred as a socket having the hollow portion, and the spigot is a solid rod. Solid rod is this is the one inserted in this one. After making joint, one rectangular hole is creating here. Through that hole, the cotter is inserting. So cotter is taking the help to joining purpose. So that's the reason name is given socket and spigot cotter joint. Okay. Generally, this type of joint is subjected to the maximum times the tensile load is generating apply subjected to tensile load application, and sometimes the load is applied here compressive type of load depends upon the position, right? So here in socket and spigot cotter joint, the design procedure now I am discussing. Design procedure is nothing but here it is a failure mode. I'm discussing whatever the design procedure, that is a one kind of failure mode. It means this criteria, that all criteria now I'm discussing, that all criteria are nothing but designing. I mean the component is going to fail in which criteria that I'm estimating. Based on that estimation, I'm going to calculate in the physical parameters. Calculation of physical parameters are nothing but designing the object. So I'm calculating the design parameters based on the permissible stresses values. Okay. So by considering the permissible stress values, I'm designing the physical parameters. Physical parameters means the diameter, length, thickness, width. These are all physical parameters, right? These physical parameters I'm calculating based on the permissible stress values, right? So that reason the whatever the physical parameters I'm calculating based on the different failure modes, failure criteria, that all are nothing but design of the socket and spigot cotter joint, right? So the first one, the first failure mode or first failure criteria, failure of the rod in a tension, failure of the rod in a tension. So this is the figure. So the first image you can find, this is the socket assemble of the socket and spigot cotter joint, right? So due to the application of tensile load, due to the application of tensile load application, there may be chances of failure of the rod. This one is called socket rod, right? So there may be chances of failure of socket rod, right? So what happens? Failure, it means there will be a induced shear stress is sorry tensile stress is going to induce. Due to the tensile stress induces, the failure is going to appear, the image is appearing on the screen. Okay. So this red color portion here, the red color portion only we need to consider for design purpose separately. I have shown on the screen at the top. That is the second image, right? So in examination, you need to write this title: failure of the rods in a tension, right? So after the writing this title, immediate right side of this title, this diagram, the second diagram you need to draw. This one you need not to draw this one, because I have shown here, because for your understanding purpose, you need not to draw this diagram in examination. This one you need to draw the second image. Okay. So the failure cross sectional area I am considering here. So what is the reason here failure occur? The reason is due to the application of tensile load. When we are applying the tensile load, there will be a tensile stress induces, right? So tensile stress. What is the tensile stress? Tensile stress basic equation. Stress is equal load by area. What type of stress I am telling? Tensile stress I am telling. So that because of what reason? Because of tensile load, right? So this is the basic equation I'm taking. Now with this equation, I can write F suffix small t equals sigma t into area. So this equation we can also call as a tensile resisting force for the rods. Tensile resisting force for the rods, right? Now tensile stress is the permissible limit we are going to take from that question. Now what is the area? The area, if we see the figure, what is the figure is appearing? A solid circle, a solid circle. So for the circle, what is the area? Pi by 4 into its diameter. Its diameter is a d. D is the diameter of the rod. Okay, pi by 4 into d square. So F suffix t equal sigma t into pi by 4 into d square. This is the equation we called here tensile resisting force for the rod. Okay, with this equation, d is going to determine. D is determined. D is determined. The answer is in mm. Right? This is the first to failure criteria. Otherwise, first to failure mode of the this Cotter joint. Right? Now, second one. Second one. The second point is failure of the spigot in a tension across the weakest section. So this is the rod inserted inside the first image. If you see the first image, this is the blue color portion. The blue color rod is the spigot rod inserted in the socket, right? So because of the tensile load application, right? So you can observe one white color line is appearing here. One white color line is appearing here. That is the failure line. It means here the title itself indicating Spigot is going to fail in tension across the weakest portion. Where? Across the weakest portion. Where is the weakest portion? Where we created the hole. Here the hole is created for accommodation of the cotter, right? Due to the application of this one, more stresses are going to induces here. More stresses are going to focuses here, right? So due to that reason, the failure is going to start here. Okay. So continuously the load is applying, the failure is happened that you can see in the second image, right? In second image, you can find the how the failure is happened for this spigot rod across the weakest portion, right? So this red color portion, this one in second image, I'm drawing the hashed lines. This red color portion only we need to consider for the failure area that I'm drawing in the third image here separately. In examination, you need not to draw the first image and the second image. Only the third image you need to draw in examination. Now, D2 is the diameter of this spigot rod and T is the thickness of the slot. Thickness of the slot. The thickness of the slot is equal to the thickness of this cotter, right? So this is the a hole is created. So that reason here there is no failure. We cannot. Here this red color portion, right? Now, what is the reason here the failure is happening? Because of tensile force applying. So tensile force we are applying, so that reason the tensile failure is happening. So inside the tensile stress is induced. Inside the tensile stress is induced. What is the equation? Basic equation, force by area. So what type of stress is acting here? Tensile stress acting. Due to the what reason? Due to the tensile load applying. So tensile load, tensile load, tensile failure, right? Now this equation I can write as Ft equals sigma t into area. Now, what is the area? Failure area only we need to consider. What is the failure area? This red color hashed portion only the failure area, right? This red color hashed portion only the failure area. Now, tell me the area of this figure, whatever the appearing, the third image, area of the third image, area is pi by 4 into d2 square minus d2 into t. This is the area for this image. Are you getting, Babu? From the solid, this white color portion I'm removing. That is, this is the solid area minus this is the hollow portion. So pi by 4 into d2 square minus d2 into t. That is, I'm writing here ft in equal sigma t into pi by 4 into d2 square minus d2 into t. Right? So with this equation is called here tensile resisting force for the spigot rod, right? Now with this equation we are going to calculate d2 value. D2 is determined in mm. Now in this case thickness of the cotter, in this case thickness of the cotter is considered as a d by 4, where d is the diameter of the rod previously we calculated, right? Sorry, not diameter of the rod, this is the diameter of the spigot rod, d2 by 4, right? And now the third point, this is the third point, failure of the rod or cotter in a crushing. Failure of the rod or cotter in a crushing. So you can find in the first image, failure of the rod or cotter in a crushing. So this is the cotter, this is the rod. So here the colored portion you can find, the colored portion. In this manner, it is subjected to the crushing. This crushing same we can find on uh, the surface of this side surface of the cotter. Okay, I am drawing this side because it is invisible. So same manner, same image is going to appear on this side, right? So you can find the another color portion here. So this is also this side, in this side also you can find this color. This colored different colors are the crushed areas. Okay, so crushing, I'm separately drawing the figure here. One circular is there and this is the one, right? In this region it is subject into the crushing. So this is the diameter is d2, its thickness is t, right? Now crushing, here the title is crushing failure is happening due to what reason? Because when it is pulling outside, when it is pulling outside, the because of this cotter, the cotter is going to hit this surface and hit this surface. So that reason, because of hitting, the inside surfaces are going to subjected to the crushing. So crushing I'm telling. So the reason crushing stress is induced. Crushing is there, stress is induced. So basic equation, stress is the equation, stress equal force by area. So crushing C I'm writing, so that reason I'm writing the C here. So that is Fc equal sigma C into A. So what is the area? The area from the figure, from this figure, area is d2 into t. From the figure, the area is d2 into t. So that area I'm writing here, Fc equal sigma C into d2 into t. This equation is called crushing resistance for the spigot rod. With this equation, sigma c is determined. Sigma c is determined. And after determination, checking is going to done. Checking is going to done. What checking? Induced crushing stress should always less than the permissible crushing stress. This condition should satisfy our answer. Then only our design is under safe condition. Right? This is the third point. Now fourth point. What is the fourth point? Failure of the socket in tension across the weakest portion. Across the slot is nothing but weakest portion. Right? So see here in the first image, due to the application of the tensile load, due to the application of tensile load, see at the weakest portion, where is the weakest portion? Where we created the hole for insertion purpose of the cotter. This is the weakest portion because while applying the force, the stresses are going to generated or gathered more at this portion only. Due to this reason, crack is going to generated here. White color line you can find. Cracks are going to generated. So based on this crack, the failure is going to develop. In second image, you can find the failure. In second image, you can find the failure. So here the red color portion. Here the red color portion only the failure area we need to consider. Right? This failure area separately I am drawing here in the third image. In the third image, the failure area I am drawing. In examination also, you need not to draw this first image and the second image you need not to draw. Only the third image you need to draw. The third image you need to draw, that is very important, right? So failure is happening in a tensile. So that reason, the reason because the reason is tensile stress is induced. Tensile stress equal tensile force by area. Now with this equation, I can write Ft equal sigma t into area. What is the area? Failure area we need to consider here. So which one is the failure area? This red color hashed line, red color black hashed line. This is the failure area we need to consider here. So now the area is I'm writing here for this image. Third image I'm writing the area pi by 4 into d d1 square minus d2 square minus d1 minus d2 into t. I'm subtracting the from whole. This is the hollow circle. So that reason pi by 4 into d1 square minus d2 square. And here one white color gap is there. Here white color gap is appearing. Right? So that reason first I'm subtracting the d1 minus d2. Then I will get these thickness values, this width values, and the width thickness is the t. d1 minus d2 into t. This is the area. So I am writing the area here. F suffix t equal sigma t into pi by 4 into d1 square minus d2 square minus d1 minus d2 into t. Now this equation is called here, the equation is called tensile resisting force for the socket across the weakest portion, right? With this equation, d1 is going to determine. d1 is determined. With this equation, d1 is determined in mm, right? This is the fourth point. Now fifth point. What is the fifth point? Failure of the cotter in a shear. Failure of the cotter in a shear. So you can see the how the failure is going to appear because of the applying the load on a cotter joint. Because of the applying tensile load, see this load is going to distributed over the socket in this manner, and on spigot we are applying the load. This is the load is going to appear here. Okay, so this is the first image. So that's the reason half of the portion is going to carried, this half of the portion is carried along the socket, and the middle portion is going to carried away by the middle portion, that is the spigot. So in the second image you can see that the top portion, the first portion, this the third portion is going to coming along the socket, and the second portion is going to coming outside from the spigot, right? Now here, while coming outside, the failure area, the red color portions appearing, failure area. So the failure area separately I am drawing here in the third image. In examination, you need not to draw the first image and you need not to draw the second image. Only the third image you need to draw. The third image you need to draw. Better if you draw the second image also, because easily we can draw, right? Now see this one, the failure is a area appearing as a rectangle, right? Now shear is happening here. So the reason shear stress is induces. Shear stress means basic equation, force by area. So because I'm writing S here, I'm writing S also here. So F suffix S equal sigma S into A. So what is the A here? The A is a failure area. The A is a failure area. Failure area I'm considering. So this is the red color hashed line is a failure area. I'm writing the area for this one. What is the area? So this is the width. This is the width B, right? And this is the thickness T, right? Now area is the B into T. Now B into T for the one shear. Here in this figure, two shear failures we can find, where at the bottom of this one, here one. These two combines one failure, and here from this failure combines one. Total two failures we are observing. So that reason I am multiplying with the two, right? So Fs equal sigma s into 2 into B into T, where B is the width of the cotter, T is the thickness of the cotter, sigma S is the permissible shear stress, Fs is the shear force or shear resistance for the cotter, right? With this equation, I'm going to calculate here B. That is, B is determined in mm. B is determined in mm, right? Now, now the sixth one. The sixth one is failure of the socket collar in crushing. Failure of the socket collar in crushing. See his image, due to the tensile load application, due to the tensile load application, this cotter is going to hit the surface of the this collar. This is the this one, this top portion is called socket collar. Okay, so we are discussing about the socket collar failure, right? So this cotter is going to hitting the surface of the socket collar, right? In this manner, it is going to hitting. So that's reason here behind this cotter, one red color shape is appearing. The color is appearing red color, right? So this red color is referred as here failure area. Separately, the separate I am drawing here in the second image. This is the second image. Separately, I'm drawing here. So separately, I'm taking out the this socket collar, and due to the hitting of this cotter, due to this hitting of the cotter, the failure area I'm drawing here. This is the failure area, right? So what is happening here? Crushing is happening. Crushing means crushing stress is induces. Crushing stress is induces. So crushing stress equal crushing load by crushed area. So crushing load equal sigma c into crush area. Okay. So what is the area? The area only there the hashed portion only we need to consider as a failure area. Other area we should not consider. If you consider the other area, you will not get the answer, because where the failure is happening, that failure only we need to consider, not the all the things we need not to consider, right? So the failure area I'm writing, the failure area here D2, says here, this is the outer diameter D4, okay? Only this particular rectangle and this particular rectangle I need. So that reason, this one I know T, this one I know T, but I don't know this width value, this width value. To get this one, I am subtracting the d4 minus d2. d4 minus d2. This is the failure area. Are you getting, Babu, how I'm writing the failure areas, right? Only this rectangle, the top rectangle, bottom rectangle I need. So this top rectangle and this bottom rectangle I need. So this one I know based on the quarter thickness, I will come this with the t value, but I don't know this width values. So this where to get this width values, I'm subtracting the from larger circle to minor circle. That is d4 minus d2, right? Into t. So this area I'm writing here, f suffix c equal sigma c into d4 minus d2 into t.
Area into 2, no, sir.
Area is not area. 2. Why we require the 2 value here? See, I'm subtracting from the top circle to minor circle. These thicknesses will going to automatically generate, right? Now, automatically, this is the t value. Why we multiply with the 2? Need not here. Okay. So here FC is the called here crushing resistance for the socket collar. Crushing resistance for the socket collar, right? For the socket collar, right? Now with this equation, I'm going to calculate the D4. Nothing but D4 is determined. D4 is determined. What is D4? D4 is the diameter of the socket collar. D4 is the diameter of the socket collar. Are you getting go? What is D2? D2 is a D2 is the spigot diameter. D2 is the spigot diameter because in this hole in D2 only the spigot is going to inserted. It means the inner diameter of the socket, outer diameter of the spigot both are equal. The inner diameter of the socket, outer diameter of the spigot both are equal, right? So D4 is determined in mm. This is the sixth failure. Now seventh failure criteria. Seventh failure criteria. What is that? Failure of the socket end in shearing. Failure of the socket end in shearing. Which one is a socket end? This is a socket collar is the socket end. Socket collar is the socket end. In this collar is going to fail in a shear. So see here, because of application of tensile force, because of application of this tensile force, and there may be chances for the failure in this region. See here, you can find the white color lines here. It means the cutter is coming outside directly with solid, right? This is the first image. Now after while coming this outside directly, you can see the image here how the parts are coming outside from the after failure is okay. Now this coming outside, the second image is on the whatever the parts is coming outside, this red color portion and the inside white color portion is appearing. These are the failure areas. Okay, this one I'm drawing here in the third image. The third image. Okay, so this is a width. This width of the collar is denoted by C, and the its socket collar socket spigot rod diameter is a D2, right? And the socket the spigot diameter is D2 and socket diameter is a D4, right? So here I written on the third image D2 D4 C. Now shearing, I'm telling the shearing here. Failure is happening in a shear. So that reason there will be a shear stress induced, that is shear force by shear area. With this equation, I can write Fs equal shear stress into shear area. What is the area here? The area is from this third image, I'm writing the area. From the third image, I'm writing based on third image, I'm writing the failure area D4 minus D2, D4, D4 minus D2 into C, right? So these failure areas are appearing both sides. It means, see, if you go through this figure, second image, here the failure area, Here on this surface one failure area, and on this surface another failure area, right? Two failure areas are appearing, so that reason here multiplying with the 2, right? So that is fs into sigma s, fs equals sigma s into 2 into d4 minus d2 into c. Okay, so one thing we can also say here, why I am writing 2, because here one part is coming outside, here another part is coming outside, two parts are failure is happening here, so that reason 2 I can write here, right? So this equation is called shear resisting force for the socket collar, right? With this equation, C is going to determine. C is determined in mm. Okay, what is C? C is the thickness of the socket collar. C is the thickness of the socket collar, right? Now the next point, eighth point. What is the eighth point? Failure of the rod in tension. Failure of the rod in a tension. Failure of the rod in tension. So the first images C you can find, because of the tensile load applying, the cutter is this cutter is coming outside of this spigot rod. So while coming outside, these white color images, the white color lines, you can find the failure is going to taking place, right? That failure is going to, you can see easily in the second image, the cutter taking this rod material outside of this spigot rod. Okay, now this failure area we need to consider. In examination you need to draw this third image. In examination you need to draw this third image, no need to draw the second image and first image. Okay, now shear, I'm telling shear because the reason shear stress is induced, right? Shear stress induced, it means shear stress equals shear force by shear area. So shear force equal shear stress into shear area, right? So what is the area here? Rectangle portion. The area is d2 into a, d2 into a, right? Now the failure area we can find this side and we can find this side also. Okay, otherwise this is the one surface, behind this another surface. Two failure areas are appearing, so that reason 2 I multiply, right? Now fs equal sigma s into 2 into d2 into a. This equation name is called here shear resisting force for the socket spigot rod, right? Now with this equation a is going to determine, a is determined in mm, right? Now the next one, ninth one, failure of the spigot collar in a crushing. So you can see the image here, the first image. Due to the application of the tensile load, this socket pushing this cutter this way, outside direction. But because of the cutter is there, so that reason it is not going to move. So automatically when these two surfaces, this the socket collar, the socket collar and the spigot collar, both are going to subject into hitting, means both are going to hit each other. So the red color portion is the failure area. Okay, this failure area separately I'm drawing here in the second image. In the second image I'm drawing the failure area, right? So this larger circle is called D3, the smaller circle is called D2. Nothing but D3 is the diameter of the spigot collar, D2 is the diameter of the spigot, right? Now crushing, I'm telling the crushing here. So crushing stress induced here due to the this hitting to each other. Now crushing stress is equal to basic equation, force by area. So because here I'm writing C, here also I'm writing C, here also I'm writing C. So Fc equals sigma C into AC. So what is the AC? Crushed failure area only we need to consider. The failure area you can find here in second image. So what is the area here? The area, only red color portion only the area we need to consider. This second image you need to draw in examination, right? So that is pi by 4 into d3 square minus d2 square, because it's a hollow circle. So d3 square minus d2 square I'm writing. So that I'm writing here fc equal sigma c into pi by 4 into d3 square minus d2 square. This equation called here crushing resistance for the spigot collar. Crushing resistance for the spigot collar. With this equation, I'm going to calculate the diameter of the spigot collar. The diameter of the spigot collar, that is D3, is determined in mm. Okay, this is the ninth one. So next one, tenth one. Tenth one. What is the tenth one? Failure of the spigot collar in a crushing. Sorry, in a shearing. Failure of the spigot collar in a shearing. So see here, the first image you can find the collar shearing off and coming outside. So in second image, how it look like if coming outside, this is the image. Okay. So this image half portion, cross-sectional image I have drawn here is the third image. Okay. The cross-sectional image means this one I'm cutting here. This one I'm cutting here. Right. After cutting, the whatever the portion is appearing, this portion I have drawn on the screen. In examination, you need to draw the third image. You need not to draw the second image and first image. The second and first images I have shown here for your understanding purpose. The all third images, whatever I have shown here, the third images only you need to draw in examination, right? The third image. Now here shearing is happening due to the reason of shear stress is induced, that is shear force by shear area, right? Shear force equal shear stress into shear area. This equation I'm modifying here, that's all. This is not new one, right? So what is the shear area? The shear area, see this hashed lines only the shear area. Okay, what is the area? D2 into T. D2 into, sorry, this is the T1, not T. This is the T1. D2 into T1. T1 is the thickness of the spigot collar. T1 is the thickness of the spigot collar, right? This is the area. Now I am writing here Fs equal sigma Fs into D2 into T1, right? This equation called here shear resistance for the spigot collar, right? With this equation, I am going to calculate here T1. That is nothing but T1 is determined. T1 is determined in mm. This is the 10th one. Now the 11th one. Failure of the cotter in a bending. Failure of the cotter in a bending. So bending, well, the cotter, while applying the load in this manner, so the forces acting on the cotter look like I have shown on the image on the screen, right? So here I'm drawing the one top view. Drawing the top view. This is the T and this is the B. This is the B. Okay, and this is the reference axis. Now bending, here I'm telling the bending. So the reason bending stress is going to induce. So bending stress means bending moment by section modulus. Bending moment by section modulus. So what is bending moment here? The bending moment, see bending moment, see here on this cotter, one side uniformly distributed load, another side uniformly varying load both sides, right? So uniformly varying load both side, one side, another side is uniformly distributed load. So this uniformly UVL load I'm converting into point load. This is the point load, right? Now this is the UDL load converting into point load. So bending moment I'm writing finally. Bending moment P by 2 into 1 by 3 into D4 minus D2 by 2, D4 minus D2 by 2 plus D2 by 2 minus P by 2 into D2 by 2. This is a bending moment. Now, what is section modulus? Section modulus means I by Y. So I means bending area momentum of inertia, that is T into B cube by 12. Y means B by 2. So B by 2 means 2 by B. So 6, this is a square. That is nothing but TB square by 6. So that is I am writing here P by 2 into 1 by 3 D4 minus D2 by 2 plus D2 by 2 minus P by 2 into D4 by 2 divided by TB square by 6. So finally, bending stress, the final equation is, if we simplify this one, P into D4 plus D2 by 2, D2 by 2 by 2 into TB square, right? With this equation is called here induced bending stress. With this equation, induced bending stress is going to calculated and check with the permissible bending stress. That is, permissible bending stress should satisfy this condition. Then our design is safe. Now the 11th point, the other design points are: length of the cotter is 4D, taper is 1 in 24, and the draw of the cotter generally 2 to 3 mm we need to take. Draw means the additional material at the top and bottom. If the rod or cotter made of same material, that is steel or worth iron, then this is the condition you need to remember. Shear stress is equal to 0.8 times the tensile stress, and the crushing stress is equal to 2 times of the tensile stress, right? So this is the design procedure asked for the 15 marks question.